Now, one of the main applications of looking at the frequency response of a circuit is to think about filters and use Laplace to analyze filters through the transfer function. So remember, the transfer function is the ratio of output voltage over input voltage. Now, what does a filter circuit actually do? It selects certain frequency ranges of your signal to pass through, and it blocks other frequency ranges. So here are, first of all, some examples of ideal filters. Now let me talk a little bit about the characteristics of ideal filters. Now here we've plotted the magnitude of the transfer function. So we've done this frequency analysis approach. We've basically taken S, we're going to let it go to j omega, and then we're going to find the magnitude of S and the phase of S. So, or the magnitude of H and the phase of H. So S has gone to j omega here, and we're going to find the magnitude of the transfer function. So we're finding magnitude of output over input as a function of frequency. So there are a few things here to talk about. This first figure, figure A, is a low pass filter. What that means is that for the ratio of the output or the input, you get something non-zero at low frequencies and you get zero at higher frequencies. So let's look at some definitions. First of all, let's talk about what it is that makes this filter ideal. So one thing that makes it ideal is that the magnitude of output over input is equal to 1 in what we refer to as the pass band. So the pass band is the frequency band that's actually being allowed through the filter. It then has so that's one thing about ideal filters. In the pass band, their magnitude is equal to 1. In the stop band, their magnitude is equal to 0. And the transition from frequencies it's passing to frequencies it's not passing is vertical. So you pass everything to the left of this line, and you cut off everything to the right of this line. So the pass band and the stop band. Pass band frequencies go through, stop band frequencies are stopped. Notice that the magnitude in the pass band is 1, and notice it is flat throughout the entire pass band. So frequencies very close to this vertical line, the output over input voltage has the same ratio as frequencies very close to 0. And in the stop band, it's all 0, and it's flat in the stop band as well. So flat in the pass band, flat in the stop band, abrupt transition from pass band to stop band, magnitude of 1 in the stop band. So that's what constitutes an ideal filter. Omega C is defined as the cutoff frequency. It's the frequency at which you transition from the pass band to the stop band. As we said, in an ideal filter, this is an instantaneous transition. We can't actually build or realize an ideal filter. In fact, you can't even simulate an ideal filter, but you can get close. All right, this is referred to as a low pass filter because it is giving you an output or passing frequencies that are below the cutoff, and it is cutting off or stopping frequencies that are above the cutoff. So this is a low pass filter here in figure A, an ideal low pass filter. Figure B illustrates an ideal high pass filter. So in a high pass filter, we are cutting off lower frequencies, we're passing higher frequencies. It has, you'll notice, all the same characteristics that make it an ideal filter: flat in the pass band, flat and 0 in the stop band, 1 in the pass band, abrupt transition. Low pass filters are often used to filter out higher frequency noise. Sometimes the high frequency doesn't mean very high. Sometimes it can mean like 60 hertz if you've got a lot of 60 hertz noise and above. Other times it can be electronic noise or environmental noise or other kinds of signal noise that appear on your signal that is not relevant to the physical problem or to the transmission of the information. So you want to cut off the higher frequencies. A high pass filter is often used if you have problems with low frequency drift or very low frequency signals superimposed on your signal. DC drift is a common thing if you have a ground and it's not like a hard earth ground. Sometimes grounds can do what we call float. They can move a little, so you get a little bit of very low frequency DC drift in your signal. That's not that uncommon, and so the passband can be used to stop DC. Also, often used if for whatever reason you're going to integrate your signal. You don't want to integrate a constant, so you would want all those low frequency signals to be gone. So that would be your high pass filter. We use a high pass filter in my lab on the EEG system because it is not uncommon for the amplifiers in the EEG to do a little bit of low frequency drift, and so we want to eliminate that from our signal. A passband filter is something that accomplishes both. It has a range of frequencies with two cutoffs, omega C1 and omega C2. The stop band is on either side of those cutoffs. The passband is in between. And so this is probably the most common kind of filter used in signal processing, this and the low pass, because typically this will reduce the high frequency noise. It'll also provide some protection against very low frequency signals as well. And then finally we have the stop band. In this case, you're passing everything except a finite or limited range. This is most commonly used to do something like block 60 hertz noise. You try and make this a very narrow stop band so that if you have a lot of 60 hertz noise in your lab that's interfering with your measurement, you can design a filter that'll act to stop that. So once again, all of these filters illustrated here are ideal. We most often look at the magnitude when we're just trying to get an intuitive feel. When you get to actually looking at communications and information transmission, suddenly the phase becomes extremely important because you're often doing something to the signal and then regenerating it. So at that point, phase information is also particularly important. But a lot of times people look at a phase curve and this doesn't mean anything intuitive, so they look at instead at the magnitude curve. Okay, so basically your axis is the frequency axis. It's important to point out that this has units of radians per second. Typically specifications are given in hertz. So you're going to have to, if you're going back and forth between designing filters and looking at specifications, you're going to have to be sure that before you work on your filter design in the Laplace domain that you are working in radians per second. So that's just a heads up. All right, so let's look at a practical application. So this is an RL filter. And we're saying if we take the output across the resistor, that this is a low pass filter. So let's think qualitatively about why that would be so. So remember the impedance of an inductor is SL, and if we let S go to J omega, we have J omega L. So if as omega approaches 0, then basically the inductor looks like a short. So all of the voltage at DC will appear across the resistor, meaning we are passing that ultimate low frequency voltage. Now as omega increases, then we begin to get a little bit of an impedance here and we get a voltage drop. So not all of the voltage will drop across the resistor, but still a significant portion of it will. Now there comes a point when we let omega go to infinity. So visualize here that omega goes to infinity. If omega goes to infinity, this impedance across the inductor, which is now an inductive impedance, becomes infinite because omega becomes infinite. So the inductor at very high frequencies looks like an open circuit, which means that all of the voltage will drop across the inductor. No voltage will drop across the resistor. So we are completely cut off as far as our output voltage when we're at very high frequencies. So looking at like a mathematical model of this, we have our voltage source, we have SL, we have R. We find the transfer function, which we found in the lecture on transfer functions. And so we put it in the form where we have RL over S plus R over L over S plus R over L. And then we substitute in our methodology to find the frequency response of a circuit. We substitute of a transfer function. We substitute j omega for S. So just as a reminder, remember S in Laplace is actually a complex frequency, sigma plus j omega. And remember in the transform variable we have e to the minus st. So the real part of S would be like a transient effect, and the j omega part will be the oscillatory or frequency effect. So essentially, when we substitute j omega for S, we're looking at the frequency response, and we are not concerned with transient effects in our circuit. So, this has two parts, a magnitude part and a phase part. So we can find the magnitude part here. We find the phase part here. At this point, I want to pause and tell you that you do need, given a complex function, to know how to calculate the magnitude and phase of that function. And you will need to be able to calculate it as a function of a variable. In this case, the variable will be omega. So if that is something you haven't done in a while, or you never quite figured out how to do, now is the time to review. And if you need resources on reviewing that, then let me know. Well, if you plot that, if you plot the magnitude of H, you come up with a curve that looks like this blue line. And if you plot the phase, you look like this blue line. And notice this is far removed from our square or rectangular ideal filter. So our ideal filter would look like these dashed lines. So we have to first of all realize that when we build an RL series filter, it's a pretty crummy filter. First of all, this solid blue line, it's not flat in the pass band. It's not flat in the stop band. There's no clear transition to define cutoff frequency. So part of what we have to do is figure out how do we define the cutoff frequency. The cutoff frequency is defined as the half power point. So in other words, your signal out, once it drops below half of the power of the signal in, then you say you're in cutoff. Now remember, power is proportional to voltage squared. So if the power out is half of the power in, then the voltage out would be the square root of the voltage in. So it'd be 1 over the square root of 2. So rather than 1/2, it's the square root of 1/2 because power is proportional to voltage squared. So the cutoff frequency is defined as the frequency at which the magnitude of the transfer function is 1 over the square root of 2 times its maximum value. Now, usually that means 1 over the square root of 2 times 1. But we can have filters that are what we call loaded, and that's part of the problem with not using an op-amp in a filter, is that if you now put something on the end of your filter to receive the signal that's coming out, you load your filter, and so this 1 is kind of a maximum and ideal value. And so in practice, often this is slightly less than 1. However, what happens then is that the whole curve just shifts down by an equal amount. So your cutoff frequency is still at the same place, but if your maximum here was like 0.9, then your cutoff would be 1 over the square root of 2 times 0.9. So you're concerned about where do you see this drop where you are 1 over the square root of 2 of your maximum value of your transfer function. Okay, so that's what the curve actually looks like. So this is a comparison between ideal filter and crummy filter. So this basically just says what we said before. Okay, so let's look mathematically at those two equations on the previous page. So we talked a little bit about qualitatively why we would expect the LR filter, the series RL filter, when we take the output across the resistor, to look like a low-pass filter. Now let's talk about it quantitatively. So I want to go back and let's look at this equation. So notice in your magnitude equation, when omega is 0, the magnitude of the transfer function is 1. And so notice then, as omega increases, the denominator increases, which means the magnitude of the transfer function is going to drop below 1. Eventually, when omega is much, much greater than R over L, then basically omega dominates the denominator and is so much greater than R over L that the magnitude of the transfer function is approaching 0. So we can see mathematically what's happening with our transfer function. So when omega is 0, denominator and numerator are equal, the magnitude is 1, the input voltage is fully passed to the output terminals, there's no change in the magnitude. As it increases and the denominator increases, the magnitude decreases in increasing amount as the frequency increases. And then finally, as omega approaches infinity, the denominator approaches infinity, and the magnitude of the transfer function goes to 0. Okay, quantitatively, we define the cutoff as where the magnitude of the transfer function is equal to 1 over the square root of 2, assuming that our max, as we found here, is 1. So the magnitude of the transfer function is 1 over the square root of 2. We set that equal to the transfer function, and what we're solving for is omega c, the cutoff. So if you set these two equations equal, that occurs when omega c is equal to R over L. So the cutoff frequency for RL filters is R over L. So here's an example on the design of an RL filter. So this is talking about electrocardiograms and saying that we want to filter out noise above 10 hertz and pass signals that are near 1 hertz. And then we want to compute the magnitude of the output voltage at 1 hertz, 10 hertz, and 60 hertz. So if we work by designing our cutoff to be right at 10 hertz, the first thing we have to do before we do anything else is we have to figure out what is that in radians per second. The next thing we have to do is we have to find out, we're not given anything about our values of R and C, we're asked, or R and L, we're asked to choose those. So if you look in the appendix of the book, you find that it's commonly available to find a 100 millihenry inductor. Now, does that mean that that's going to work as my final solution? Maybe not. I may need to tweak that a little bit if I find out it gives me an unreasonable value for R. So once again, design problem is sort of iterating between, the question and answer. So here is our omega cutoff when we convert to radians per second. If I use 100 millihenries and then use the relationship between the cutoff being R over L, I can solve for the R that would give me the correct cutoff. So now what I want to do is I want to plug in those numbers. So I plug in the numbers for R over L, 20 pi, which is my cutoff frequency anyway, and I come up with this equation for the magnitude of the output voltage. So given that equation for the magnitude of the output voltage, I can then start plugging in values for omega and actually calculating numbers. So when you plug in 1 hertz, which would be 2 pi, you have an input of 1, you get an output of 0.995. We check 10 hertz, we get an output of 0.707. We check 60 hertz, we get an output of 0.164. So this basically is in tabular form, what would look like the curve that we plotted in blue at the beginning of this lecture.